recording is working some problems on the content that you've looked at in Chapter 10. First off, let's consider the concept of acids and bases according to the definition given to us by Bronsted-Lowry. An acid is a substance that loses a hydrogen ion in a chemical reaction, and a base is a substance that gains a hydrogen ion in a chemical reaction. So we're basically looking for H plus being moved around. So that means we need to check the number of hydrogens in each of our substances. So we start on our reactant side and see I have one H here and I have two H's here. And my two H's, let's actually use a different color here. That'll make it. I have two H's here. And then water on the product side becomes H3O plus, and so now I have three H's. And HClO becomes HClO minus, and I have zero H's. So HClO started with one H and ends with zero H's. And H2O started with two H's and ends with three H's. So I can see that the HClO lost a hydrogen, and so therefore it is the acid. And I can see that water gained a hydrogen because it started with two and it ended up with three. So therefore water is considered the base. Now this problem doesn't ask for it, but it's good to note who my conjugate acid and my conjugate base are. H3O plus, if we look in reverse, starts with three hydrogens, ends up with two hydrogens. That's my conjugate acid. And that makes ClO minus my conjugate base, because it's the only thing left. Also, recall that your acid will always become your conjugate base, just like that, and your base will always become your conjugate acid. All right, let's look at the next problem. Here we have no hydrogens, zero hydrogens. Here we have two hydrogens. Here we have one hydrogen. And here we have essentially zero acidic hydrogens, right? Because to be an acidic hydrogen, it has to be listed in the front of the formula. So that H in hydroxide is not acidic. So OCl minus goes from zero hydrogens to one hydrogen, and H2O goes from two hydrogens to, I listed them together. Let's call this one hydrogen then. So OCl minus goes from zero hydrogens to one, so it is gaining a hydrogen. It is accepting a hydrogen, so that therefore this is the base. And H2O loses a hydrogen, so therefore H2O is the acid. That makes OH minus my conjugate base, and HOCl my conjugate acid. Next, let's write equations to show the acid-base reaction that occurs with the following Bronsted-Lowry acids and bases. So we know that our acid is H2PO4 minus, and we know that the acid will lose a hydrogen. And our base is NH3. So if my base picks up a hydrogen, then I should be losing a hydrogen from my acid. So losing an H plus here and gaining an H plus on my NH3. So if I add an H plus, if I take away an H plus from H2PO4 negative, then I only have one H remaining. I still have the phosphate, but now my charge was negative, but I've taken away a positive, which makes it even more negative. Now it's -2. For the NH3, I was adding a hydrogen ion, that should be a 3. And because I've added a hydrogen ion, I have a plus charge on this. Now this collection of things here is often written NH4 plus, which is actually what you saw me start to write before I realized I'd already put the hydrogen up front. All right, let's look at our acid. This time is water. Remember, we're going to take away, we're going to subtract an H plus from there, and our base is ClO4 -1. And for my base, I'm adding an H plus. So in this case, if I take away an H plus from water, I'm left with OH minus, because it was neutral and I removed an H plus. If I add an H plus to ClO4 negative 1, now it becomes neutral, because I was negative, and now I've added a positive, and a plus 1 minus 1 equals 0. Are these conjugate acid-base pairs? So if I have HNN3, that is an acid between these two, because it's the only one that has a hydrogen in the front of the formula. If I was to put it in a reaction with water, where I know that it's acting like an acid, then water must therefore be acting like the base. And that means that HN3 will lose its hydrogen and become N3 minus, and water will pick up that hydrogen and become H3O plus. And what we notice here is that the acid always becomes the conjugate base. So indeed, HN3 and N3 minus are an acid-base conjugate pair. Let's consider H2SO4 and SO4 negative 2. If I take my H2SO4, again, I know that this is an acid because it's got the H's listed out front. So here's my acid. And it has more H's. So if I had H2SO4 and HSO4 negative 2, I would have had to consider who had more H's. That would be my more acidic thing. So I'm just going to add it to water to see what it does, because water can act like all kinds of things. In this case, I needed to act like a base because I already have an acid. So my acid will again lose an H plus, forming HSO4 negative, and water will pick up that H plus and be H3O plus. So my conjugate acid, my acid forms my conjugate base here, and that is not the formula of the substance that we've been shown. So this is not a conjugate acid-base pair. Let's write the formula for each of the following. We want the conjugate acid of hydroxide. So think of this as, if we're asking for the conjugate acid, then hydroxide must be my base. And again, I'm just going to add it to water to see what happens. So if hydroxide is my base, then water has to be acting as my acid. And my base will gain an H plus. So that means over here I should have HOH, otherwise known as water. See how my hydroxide picked up that extra H and became neutral? And on the other side, H2O has now lost a hydrogen and it has become OH minus. So here was hydroxide. Here's what it became. And we know that the base becomes the conjugate acid. The other thing I could have done, rather than writing this out longhand, was just to recognize that OH minus plus an H plus should give me the conjugate acid, which would be H2O. Okay, the conjugate base of ammonium. Ammonium is NH4+. And what's sneaky about ammonium and why we're doing this as an example is ammonium is really HNH3+. This has one acidic hydrogen. So if I'm asking for the conjugate base, then that means ammonium is acting as my acid. And if I add this to water, then we'll see, oh, my acid will lose a hydrogen and make NH3, and my base, which water had to be, will gain a hydrogen, making it H2O+. Since my acid becomes my conjugate base, the conjugate base of ammonium must be NH3. The shortcut way to do this is to recognize that NH4+ is the acid, and just taking away one hydrogen, minus H+, would give me NH3, which is my conjugate base. So you can do it either way. Write the two equations needed to describe the behavior of the following amphiprotic substances in water. You remember, amphiprotic means something will act either as an acid or as a base, so it has the capability of doing both. Water is the classic example of this, and here are two other substances. So we need two equations, one when it acts like an acid and one when it acts like a base. So let's start with H2PO4. PO, that should have, I think should have a 4. Let's put a 4 on there. So H2PO4 negative, if I'm going to act like that's an acid, then it will react with water. This is my acid. Water will act like a base then. My acid will lose a hydrogen ion, so we're going to take away an H plus here. My base will add a hydrogen ion, so we'll add a hydrogen there. And so H2PO4 negative without one of its hydrogen ions is a single H, PO4, and now my negative has gone up because I took away one of my positives. On the other hand, the H2O becomes H3O plus because it's picking up the hydrogen. Okay, let's do this as a base. H2PO4 negative now is acting as my base. That means water is going to act like my acid. And bases are going to gain a hydrogen, so I'm going to add a hydrogen here. And my acid is going to lose a hydrogen. So my base will have one more hydrogen ion than I started with. So that would become H3 from H2. And now it will be neutral because my positive added to my negative on the original ion gives me neutral. My water, however, was neutral and has lost a hydrogen ion, so it becomes OH minus. Let's look at pH 3. pH 3 acting as an acid will be going to lose a hydrogen, so it will become pH 2 negative, and water will pick up that hydrogen and become H3O plus. pH 3 acting as a base will pick up a hydrogen from water and become pH 4 plus, or you could say HPH 3 plus, either way, plus OH minus. How many hydrogens are acidic and how many are non-acidic in the following compounds? To analyze this, we want to look at where the hydrogen is located. So hydrogens listed at the front of the formula are acidic, and those listed in other places in the formula are not. So when we look at H2CO3, we see there are 2 hydrogens listed in the front of the formula, and so we would say there are 2 acidic hydrogens and no non-acidic hydrogens. When we look at the next compound, we see 2 hydrogens listed there at the front, and we see an additional 2 listed in the middle of the formula. These hydrogens listed at the front are 2 acidic hydrogens. These hydrogens listed in the middle are 2 non-acidic hydrogens. And acidic hydrogen just means it can be lost in an acid-base reaction. What is the difference between a strong base and a weak base in terms of equilibrium position? So the definition of a strong base is that, for instance, we could have some base reacting with water. Whoops, sorry, I was thinking ahead of myself there. Reacting with water. A strong base will completely pull off one of those hydrogens from water and leave OH minus. And by completely, we mean that there is lots of product, and really nearly none, if not none, or reactant. And so if we think about what we know about equilibrium constants are the concentration of my products over the concentration of my reactants. And in this case, I have lots of product and no really reactant. And so that means this top number is really large, big, and this bottom number is really small. And so we would say that the K would be big. And we would also say that our equilibrium position favors products. Now, if we talk about a weak base, it's the same reaction, only this time doesn't really go very far to the products. In fact, it favors reactants because a weak base doesn't really do much with the water. It might do a little bit of making a hydroxide, but not much. So that means I have lots of reactants, but not very much products, very little over here. And so that means equilibrium position would favor reactants for a weak base. Favors reactants. That was different than the strong base, which favored the product side. The HNO3 in a 0.5 molar solution is 100% dissociated. What is the molarity of HNO3, H3O+, and NO3 negative in solution? So what this is saying is I have HNO3, and I put it into water, and it completely splits up, and it makes H+ and nitrate ion. And this says it does this 100%. So I put HNO3 in, I get 100% products, and I have 0% HNO3 left in solution. So originally, this was a 0.50 molar solution. So at the start, we know that HNO3 equaled 0.50 molar. But as soon as we put it into solution, what happened to that concentration? Well, it went to 0 molar. There's nothing left of the HNO3. On the other hand, at the beginning, the concentration of H+ and the concentration of nitrate had to have been 0 because we hadn't done anything yet. But after the reaction is finished, well, we shouldn't say reaction is finished. We should say after we make this a solution, it said 100% dissociated. So that means all of the 0.50 molar solution of HNO3 made products. And if I started with 0.50 molar over here, then for every 0.5 molar of that, I have 1 H and 1 NO3. So I have 0.50 molar H+, and I have 0.50 molar nitrate ion. Sorry about that. Write the acid ionization constant expression for the ionization of each of the following monoprotic acids. So we're looking for the Ka here. That's what acid ionization constant means, Ka. Equilibrium constant expression, essentially for an acid dissociating. So if I have HCN, it dissociates, it makes H+ and Cn-. These are aqueous. This may be aqueous or not. We're going to pretend it is for this because I didn't write down the phase. So equilibrium constant expression is going to be H+ times Cn- over H, whoops. It's trying to write H3O+ for some reason. Let's get rid of that. HCN. Now, if instead my HCN concentration, phase was a pure liquid, good grief. Then how would things change in my equilibrium constant expression? Well, my ions over here are always aqueous because they're dissolved in water. But if this is a pure liquid, then that means that Ka will equal concentration of H+, concentration of Cn-, and we're done because we don't include the concentrations of pure liquids in the equilibrium constant expression. All right, so HC6H7O6, C6H7O6. Let's assume this is a pure liquid. We get H+ plus C6H7O6. These are aqueous. And so Ka equals the concentration of each of my products. And I'm finished because in this scenario, I made my reactant a pure liquid. Now, if it wasn't a pure liquid, then just like with my HCN example up here, then I would find my acid in the denominator. Is acid Y or acid Z the stronger acid? At equal concentrations, the percent ionization for Z is greater than that of Y. So we know that the definition of a strong acid is it completely dissociates. So if something dissociates more than something else, that means it's a stronger acid. So if they both have the same concentrations and Z% ionization is greater, then Z is a stronger acid in that case. Letter B says Ka for Y is smaller than Ka for Z. So remember Ka, we just did that on the last problem, is products over reactants. So a large Ka will go with an acid that has dissociated a lot, which is the definition of a strong acid. So Ka being smaller, Ka for Y is smaller than Ka for Z suggests that Z has a larger Ka, and so therefore it is a stronger acid. In letter C, the equilibrium position for the dissociation of Z lies farther to the left than that for Y. And so what it's basically saying here is if I have HZ dissociating to make H plus Z minus, this is going farther to the left. So the left side is favored. That means keeping HZ together is more favorable. We know that strong acids would favor the product side, so therefore Y is our stronger acid. Classify each of the following substances as an acid, base, or salt. So an acid is going to have hydrogen ion written out front, a base will have hydroxide present, and a salt will be a metal and a non-metal ions. So calcium hydroxide, this is a base. It's got hydroxide. HCN, this is an acid. It's got H written right out front. KBr, no H out front, no hydroxide. This is a salt. HCl, that's an acid. Without writing an equation, what is the mole ratio for the reaction between each pair below? So in this case, we've got HCl and KOH, and this is really getting at a neutralization reaction. And all neutralization reactions boil down to H plus OH minus making water. So I'm really looking at the ratio of how many H's do I have to how many hydroxides do I have. Since I have one of each here in this equation, I would say the mole ratio is 1 to 1. Down here, however, in the second one, I have 2 H's for 1 hydroxide. I'm going to need enough hydroxide to pick up all of those H's. So I will need 2 hydroxides for every one of my H2CO3s. So my mole ratio will be 1 H2CO3 to 2 potassium hydroxides. Write a balanced reaction for the preparation of each of the salts below using a neutralization reaction. So this is saying I have a neutralization reaction. I've got some acid reacting with some base, and we know neutralizations are a form of double replacement. They make a salt plus water. And in this first one, it says my salt is lithium nitrate. So that means lithium nitrate is my salt, and I just do a double replacement reaction backwards, thinking about water as HOH. So I end up with HNO3 plus lithium hydroxide. If barium chloride is the salt, again, thinking about water, think about it going backwards. Barium is going to pair up with the negative in HOH, which is hydroxide. So I will have barium, which has a +2 charge, and hydroxide, which has a -1 charge. So I'll need 2 hydroxides. And then hydrogen will pair up with the chlorine, and I'll have HCl and barium hydroxide. For potassium phosphate, I have K3PO4 as my salt. Go backwards. Should have KOH and H3PO4. Just think double replacement reaction going in reverse. Calculate the molarity of H0 plus in a solution if the hydroxide solution concentration is as shown below. You'll need your calculator for this. And you'll need to remember the Kw equation, which is 1.0 times 10 to the -14th is equal to the hydronium ion concentration times the hydroxide ion concentration. In this case, we've been given the hydroxide ion concentration, so I will plug this number in right there and solve for the hydronium. So 1.0 times 10 to the negative 14th. And I will divide by 5.0 times 10 to the negative 4th. Helps if you remember to do your parentheses. I get 2.0 times 10 to the negative 11th molarity for the hydronium ion concentration. Same process with the next one. 1.0 times 10 to the negative 14th divided by 7.5 times 10 to the negative 7th. I get 1.33 times 10 to the looks like I put in the wrong value. So my calculator spit out 1.33 times 10 to the 20th. I know that's wrong because if I'm taking 10 to the negative 14th and dividing by 10 to the negative 7th, my negative number should go down, but it should still be negative. So I'm going to put these back in. So 1.0 times 10 to the negative 14th divided by 7.5 times 10 to the negative 7th. Aha, 1.33 times 10 to the negative 8th. That makes a lot more sense. Calculate the pH of the following solutions. If my hydronium ion is 3.3 times 10 to the negative 5th, I know that pH equals the negative log of the hydronium ion. So I'm simply going to place this number in here and take the negative log of it. So the negative log of 3.3 times 10 to the negative 5th is 4.48, so I'm going to make that 4.5. And then the hydroxide ion, this is going to require an additional step because see how this is the pH of hydronium, not hydroxide. They are not irreplaceable, or excuse me, they are not replaceable of one another. So that means I need to know what my hydronium ion concentration is. I can use my KW equation, plug in my 8.2 times 10 to the negative 10th for hydroxide, and solve for the hydronium ion concentration. We just did this on the previous slide. I get my hydronium ion concentration equal to 1.2195 times 10 to the negative 5th. And to get the pH, I know I need to take the negative log of that number. Which is 4.91. Call it 4.9. pH. There we go. What is the hydronium ion molarity for solutions with the pH values shown below? In this case, I'm starting with pH. And we know that 10 to the negative pH equals hydronium ion concentration. So I can say 10 to the negative 2.05, and that should equal my hydronium ion concentration. And this is 0.00316 molar. And this one, 10 to the negative 4.88. It's going to be 1.32 times 10 to the negative 5th molar. And down here, we have 10 to the negative 6.75. This is 1.78 times 10 to the negative 7th molar. Solution A has a pH of 4.20, solution B has a pH of 11.30, solution C has a pH of 6.66, and solution D has a pH of 7.73. We want to know what these solutions rank in terms of decreasing basicity first. So larger pH gives me more basic. So large pH equals more basic. So my most basic solution is the one that's largest, which should be solution B. So B, and then just going down numerically, then D, then C, then A. Decreasing hydronium ion molarity is going to be a raise in pH, because as my hydronium ion concentration goes down, my pH is going to go up. So decreasing hydronium ion means I want to start with my most acidic solution, 4.20. So that was solution A. And I'm going to go up. So A, C, D, B. My last one, I have increasing hydroxide ion concentration. So I should have an increasing pH, which means I should start with A, and then C, and then D, and then B. And that's good. This matches this one, right? Decreasing hydronium ion meant I'm getting less and less acid. Increasing hydroxide ion means I'm getting more and more hydroxide. And so those two things are happening at the same time. So those should match. Acid A has a pKa of 5.71. Acid B has a pKa of 5.30. Which of the acids is weaker? So we know that the pKa equals the negative log of the Ka. And we know that big Kas equals strong acids. So if I have a pKa of 5.71, then I can either do the math or I can think about this in sort of a theoretical way. I'm going to go with the theoretical way for those of you who aren't as comfortable with the math. And then we'll do the mathematic way as well. So big Ka means strong acids. If I take the negative log of a large number, like for instance, I'll take the negative log of 0.20 versus the negative log of 0.10, we can see, I guess there is math here. Negative log of 0.1 gives me 1, and the negative log of 0.2 gives me 0.698. So larger Kas give me smaller pKas. So small pKa goes with a big Ka. So I look at my two numbers and see acid B has a smaller pKa, which means it's a stronger acid. So the weaker acid must be acid A. Predict whether each of the following pairs of substances could function as a buffer system in water. We're looking for a combination of weak acid and its conjugate base, or weak base and its conjugate acid here. In my first example, I see two acids, so I don't have any bases there, and they're both strong acids, so it's definitely not, those aren't going to act like a buffer. In the second case, I have nitric acid and, not nitric acid, nitrous acid, HNO2, and KNO2, and I see this. It helps if you don't recall, let me just make sure everybody's on the same page with me. In chapter 10, you should have a list of strong acids and strong bases. And that list can be found in table 10.1. And we see there hydrochloric acid, hydrobromic acid, hydroiodic, nitric, chloric, perchloric, and sulfuric. Aha! HNO2 is not present. That means HNO2 is a weak acid, because everybody who's not listed in my strong acids is therefore a weak acid. To be a good buffer, though, I need access to the conjugate base of HNO2. Luckily, the conjugate base of HNO2 is just the removal of a hydrogen ion, and so that should be nitrite. We look over here and see this is carrying a source of nitrite, and so indeed, this will be a buffer. In the next one, NaC2H3O2, that's acetate, so sodium acetate and potassium acetate, I don't have anything that can act like an acid. So this isn't going to work as a buffer either. Identify the two active species in each of the following buffer systems. I'm looking for an acid and its conjugate base, or a base and its conjugate acid. In this first one, I see there's the weak acid, and so I'm looking for its conjugate, and its conjugate is F minus. So I'm looking for a source of F minus, and I find it in my ionic compound. So the active species are HF and F minus. In the next one, I have Na2HPO4, and I've got KH2PO4. And I think that the sodium here and the potassium are not super important, because I can see that this is really HPO4 negative 2, and that this is H2PO4 negative. And now I can see this one has one hydrogen, this one has two hydrogens. They're both, neither of them is a strong or weak base. And so H2PO4 would be my acid, and HPO4 negative 2 would be my conjugate base. Or HPO4 negative 2 would be my base, and H2PO4 negative would be my conjugate acid. It doesn't really matter. Write an equation for each of the following buffering actions. The response of an HPO4 negative 2, PO4 negative 3 buffer to the addition of hydroxide. So hydroxide is added. It's going to react with the best acid available. I look up here and I see, no acidic hydrogens, but this one does, so that's going to be my acid. And now it's just Bronsted-Lowry. Here's my base, here's my acid. What happens? Well, the acid gives up its H. The acid gives up its H. I get H2O and PO4 negative 3. The response of an HCN-CN minus buffer to the addition of hydronium. So hydronium is an acid. It's the acidic form of water, so it's going to react with the base. HCN, it's got an H up front. That's not a base. That's an acid. So CN minus must be my conjugate base. So we know this is acting like an acid, this is acting like a base, and so we should get HCN plus H2O. Strong electrolytes or weak electrolytes? Well, I'm looking to see whether I have strong acids or weak acids, or whether I have soluble ionic compounds. H3PO4 is phosphoric acid. It's not one of my strong acids, so therefore it's not a strong electrolyte. This is a weak electrolyte. Nitric acid, however, HNO3, is one of my strong acids, so it's a strong electrolyte. KNO3, if we go back and check our solubility table in Chapter 8, is a soluble ionic compound, and so it is also a strong electrolyte, because it splits into ions when it goes into water, which is what electrolytes do. Determine the molarity of a KOH solution when each of the following amount of acid neutralizes 25 milliliters of it. So first thing we need to do in this titration problem, which is what this is to write a reaction. So I have KOH reacting with H2SO4. It's a neutralization reaction. So I get K2SO4, just using my double replacement skills here, and H2O. I'll need 2 KOHs and 2 waters. So now I look at this and see I've been given 2 pieces of information about H2SO4. So that's where I'm going to start. 5.00 milliliters, 1,000 milliliters, 1 liter. 1 liter is 0.500 moles of H2SO4. If I want to know the molarity of KOH, and I've been given the volume, then I'm missing the moles. I want the moles of KOH. So I look at this and see down here that I've gotten to moles of H2SO4. And in my balanced chemical reaction, I can see that I have 1 mole of H2SO4 to 2 moles of KOH. So then, using my calculator, I can calculate how many moles of KOH there are. I get 0.005 moles KOH, but I want molarity. So I need to divide by 25 milliliters in liters, which is 0.0250 liters. Just divided by 1,000. 250 liters. And that gives me 0.2. Check my sig figs. I see I have 3 sig figs. So I need 3 sig figs, 0.0200 molar. Finally, Similar problem, different reactants. So I have HNO3 this time, reacting with KOH. And this is a 1-to-1 mole relationship. So I have KNO3 plus H2O, and it's already balanced. So I'm given, again, 2 pieces of information about the HNO3, so that's where I'm going to start. And it's identical process. Take my milliliters, change to liters, use my molarity to change to moles, and then use my mole-to-mole relationship to change from moles of what I have been given to moles of what I want. So this is 0.005 moles. Oh, look, it's the same number of moles. And it's still the same volume. So I get equivalent molarities. Isn't that interesting? And we're finished.